Good morning, folks. This is Mike coming back at you with another voiceover of one of our previous videos. In this video, we are going to be doing live commentary on more real-life applications of linear equations. In the previous video, we talked about linear equations, what they look like, how do we solve them, what are the various types of linear equations we could have, and then solving related rational equations that are secretly linear. There's just a little bit of work we have to do with them to turn them into that nice form. So we saw in the previous video a little bit of a real-life application of them. This video, there's going to be more of a focus on the real-life applications of linear equations. So one big use of linear equations is in simple interest. If you deposit some fixed quantity of money, say P dollars, into, say, a savings account, and the savings account has an annual interest rate R that's used as a decimal. If you put it in there for T years, then the amount of interest I that you get after those T years is P times R times T. What makes it linear is that P and R are known. They're known numbers that are given to you. T is the actual variable. T is what changes. So we have some number times T, and that's what makes this a linear equation. This is sort of related to the formula for compound interest. It's not exactly the same. There is something else in there. Some of you may have seen that famous formula, A equals P times E raised to the power of RT. So this is the other kind of interest that we can have. Simple interest, just for short, is based on what you put in at the start. Compound interest is based on what your previous balance was at the end of the last time period. So here is a just sample practice problem here. If I deposit $9,000 into a savings account and my account has an annual interest rate of 3%, and I leave it in there for 30 months, how much simple interest am I going to get? So 9,000 is our P. That's how much we put in to start. The annual interest rate is 3%, but like we said, we use it as a decimal. So as a decimal, that's 0.03. And then 30 months. Well, T is measured in years, so we need to convert 30 months to a number of years. 30 months is 2.5 years. So I'm going to take the product of 9,000, 0.03, and 2.5, and we're going to see that we come up with $675 of simple interest. Just as a quick side note, if you find a savings account that gives you an annual interest rate of 3%, then definitely put your money in there. Interest rates on most savings accounts with large name banks, very, very small, a fraction of 1%, a tiny fraction of 1%. But here's more of a challenging use of these linear equations. Suppose I deposit $15,000 between two savings accounts, account A and account B. Account A has an annual interest rate of 2%, and I let the money sit in there for 21 months. However much money I put in, I let it sit in there for 21 months. While account B, which has an interest rate of 3.5%, had the money that I put in there, I left it in there for 2 years. So if the total interest that I received between account A and account B was $875, how much money did I put into each of account A and account B? So this may seem like a fairly complicated problem. Some of you may even be thinking that there's no way that we can do this with just a simple linear equation. But that's actually not true. We can do this just with a linear equation. Excuse me. We're going to use that P times R times T formula, but we're going to use that once for account A and once for account B, and we're going to add those up, and that needs to add up to our total amount of interest, which was $875. So let's let X be the amount of money that was deposited into account A. Then the interest that I gained on that money, which I let sit in that account for 21 months at an annual interest rate of 2%, is going to be X, how much I put in, times the rate used as a decimal is 0.02, and 21 months converted into years is 1.75 years. So that product is going to give me the interest I gained just from A. Since X is how much money I put into account A, and between A and B I put in 15,000, that means 15,000 minus X is how much money I have to put into account B. So that is going to be my p-value, if you will, for calculating the simple interest that I get on account B. The annual interest rate on B was 3.5%, used as a decimal, that's 0.035. And then I invested that money in that account for 2 years. So the interest I gained on account B is 15,000 minus X, that's my p-value, times R as a decimal, 0.035, times my time, 2. I was told that the total amount of interest I got between account A and account B was $875. So if I add 0.035x, which is what you get when you simplify the formula for account A, and then 0.07 times 15,000 minus x, that's what you get when you simplify the formula for the interest for account B. Add those up, set that equal to $875. So we just have a little bit of math that we have to do here. There's that same equation that we got. So 0.035x plus 1,050 minus 0.07x is going to equal 875. Combine those x terms, and I subtracted the 1,050 from both sides to give me negative 0.035x equals negative 175. Lastly, I just have to divide both sides by the negative 0.035. And when I divide both sides by the negative 0.035, we're going to come up with our x value of, drumroll, $5,000. So x equals $5,000. Again, going back to working through our problem, x was the amount of money that we put into A. So that means $5,000 was put into account A, and thus $10,000 was deposited into account B. So that's a neat little real life application of these of these linear equations. Dyslexia is fun sometimes. For the most part, though, now we do calculate using compound interest, not so much simple interest. So it's a bit outdated of a problem, but it does nicely showcase the use of linear equations in a realistic scenario. Another place that we can use linear equations is in ratios and proportions. And here's a sample problem highlighting ratios and proportions. A recipe for cookie dough calls for flour and sugar. There are 2 more cups of flour than there are cups of sugar in the cookie dough. If the ratio of flour to sugar is 3 to 2, how many cups of flour are there going to be in this cookie dough? So just like the previous problem, we are going to have to introduce a variable x in here, and we are going to have to let this variable represent the number of cups of one of these things, either the number of cups of flour or the number of cups of sugar. But we have a relationship between the number of cups of flour and the number of cups of sugar. As you can see, we underline there are 2 more cups of flour than there are sugar. And the other key piece of information that we have here is that the ratio of flour to sugar is 3 to 2. So here I chose to let x stand for the number of cups of flour. Now the problem said that there were 2 more cups of flour than there are cups of sugar. So if x is equal to the number of cups of flour, then since there are 2 more cups of flour than sugar, the number of cups of sugar is going to be x minus 2. As we can see right here. Cups of sugar is going to be x minus 2 because flour had 2 more than sugar. And then we are going to use those values, x and x minus 2. We're also going to use the known ratio that we need to have of flour to sugar, which is 3 to 2. So we have actually a rational equation here, but secretly this is a linear equation. We could go about solving this using techniques similar to what we saw in our previous video, but the technique you may be more familiar with is the method of cross multiplication. You can multiply the x and the 2 and then set that equal to 3 times the x minus 2. So this means that 2x is going to equal 3 times x minus 2, or 3x minus 6. I want to look at those 2 things. I'm going to subtract 3x from both sides to give me minus x equals minus 6. And that is going to imply then, after I divide both sides by -1, that x is equal to a positive 6. So I know that there are 6 cups of flour in this recipe for my cookie dough. Now, that's not the only way that we could have solved this problem. I chose to solve this problem this way, having x be the number of cups of flour. You also could have done it where x is the number of cups of sugar, but then that would slightly change your formula for the flour. If x is the number of cups of sugar, your number of cups of flour would be x plus 2, because we said there's 2 more cups of flour than there are sugar. And your ratios would become x plus 2 over x is equal to 3 over 2. And if you cross multiplied, you would get 3x is equal to 2 times x plus 4. You can nicely solve for x here, subtract 2x from both sides, and you find that x is equal to a positive 4. So that's the number of cups of sugar. Take that x value of 4, substitute it back into your flour, and you get 4 plus 2, or 6. So you can still come back to the same answer. There is more than one way to come up with the correct answer to these problems here. It's all this comes down to, do you do sound math and do things make sense? So for some of us, that may be a little bit sort of uncomfortable, having the sort of freedom, if you will, to sort of solve it in sort of a way whichever you choose. That may make you nervous because you may be unsure if what you're doing is right. But part of math is trying things, seeing if they work. If they don't work, then hey, go back to step one and try something else. Who knows? Maybe try something and it will work. But guys, this concludes our voiceover of our video on applications of linear equations. Again, if you have questions, reach out to me, emails, texts, postcards, whatever. Take it easy, guys.